So this video we're going to talk about real gases. So what do we mean by a real gas? Haven't we always been talking about real gases? Well, recently we've been dealing with this ideal gas equation. So it has this funny word ideal in front of it, right? Let me remind you first what we mean by an ideal gas. So an ideal gas is any gas that obeys this equation, the ideal gas equation, Pivner. So an ideal gas has to follow this equation. Where did this equation come from? Well, it came from experiments on real gases. But as we're going to see in a minute, sometimes you can have extreme conditions where this equation isn't quite obeyed. So the other thing about ideal gases is that they are described well by this kinetic molecular theory. I've abbreviated that KMT. So this kinetic molecular theory is a model, an explanation, and it turns out that if you start with that model, you can derive or prove the ideal gas equation as long as you're using a certain set of assumptions. Now there's several set of assumptions that go into specifying what our model is for the kinetic molecular theory, and here are three of them that I just wanted to remind you of. So there's some others that I'm not going to talk about. So one of the assumptions in our kinetic molecular theory is that gas particles have negligible volume, at least compared to their container. So they occupy a tiny fraction of the total volume that's available. So tiny that, well, it might as well be zero. Also, gas particles undergo elastic collisions when they bump into each other or with the walls of the container. And third, there are no intermolecular interactions. So between the gas particles, there are no attractions and no repulsions. So the molecules can buzz past each other and not really feel each other, other than when they bump into each other, they collide elastically. Alright, so let's think about this ideal gas equation real quickly. And we're just going to solve that for volume real quickly. So volume is equal to nRT over P. And let's think about what this equation is telling us. This equation tells us that if we think of the pressure and we increase that pressure, the volume is going to go down. Alright, so let's get a picture of that. So here we have a container, and I've got some sort of movable wall in the top of the container. My lid can go up or down. And I can put different kinds of weights on it. So here's a weight, a mass, that will exert different kinds of pressure on my gas. So inside this container then I have my little gas particles. So I'll just draw some little green dots. Now these are supposed to be point particles. Remember, they have negligible volume. And according to the kinetic molecular theory, we imagine that they're in constant random motion. So they're moving around, they're bumping into the walls of the container and exerting pressure. They're bumping into each other. Okay, now what we're going to do is we're going to take the same sample of gas and we are going to squeeze down on it by increasing the pressure, right? So we're going to put a much bigger mass on here, and so I've decreased the volume by putting a much bigger mass on the top of this movable wall right here. And now my poor little gas particles are contained into a much smaller volume, right? And so they are bumping against the walls much more frequently and creating more pressure. Now let's think about if we keep increasing the pressure, what does this equation tell us is going to happen? Well, it says that as pressure, that's supposed to be a P, as pressure, as we send that all the way bigger and bigger and bigger, what's the biggest we can get? Well, we can make it infinity maybe. So if we were to make this infinity, then we have some constant over infinity. Well, that's going to zero. So that means the volume is going to zero. So as we continue to squeeze this more and more and more, the ideal gas equation is telling us that our volume is going to go to zero. Well, that can't be, right? Because we can't obliterate these molecules simply by squeezing on them. We can't make them go away. Of course, they have negligible volume, but it's not zero, right? So they actually do take up some volume. And we know what happens in this case experimentally, that if you squeeze more and more and more on a gas, eventually those particles are going to come together and make a liquid. So we know that from experiment. And when that happens, this equation starts to not fit behavior very well. So that's what we mean by real gases. So real gases are gases that don't obey the ideal gas equation under all possible conditions of pressure, volume, and temperature. So these are the things that we interact with. So when does the ideal gas equation work? So the ideal gas equation is good when pressures are low And by low, I mean anything like an atmosphere or less. 1 atm or less. It's also pretty good when temperatures are high. What does high mean? Well, room temperature. So 298 Kelvin or so. Anything that temperature or higher, sometimes a little bit below. Maybe you can get as low as 273 standard temperature. Then we would expect the ideal gas law to still behave pretty well. So it won't behave well if the pressure gets really high, like in this situation up here in my box. So that's a case when we would not expect the ideal gas equation to hold very well. Or when the temperature gets very low, right? If we make the temperature low, then these molecules start to slow down a lot, and their behavior is going to be very different. Because in fact, there are intermolecular interactions. Most molecules, when you get them a little bit close to each other, are going to tend to attract each other. But if the temperature is high, they're moving way too fast for them to have time to stick together. Even if they were, imagine tennis balls covered in Velcro. If you're throwing them at each other at really, really high speeds, they're going to ricochet, even if they have Velcro, hook and loop kind of stuff on them. All right, so there's not enough time then when you're at high temperature. But at low temperature, they have time to sort of stick together, and they begin to condense into a liquid, right? So we know that's going on. Let's look at some more experimental data. So here's some experimental data, but first let me tell you about these axes that I've drawn on here. So this is pressure. So we're going to look at what happens as we increase pressure. Now let me tell you about the y-axis. So if we take a Pivnert equation right here, we're going to solve this. We're going to rearrange the variables so that they're all on one side. So I'm going to divide both sides of this equation by nRT. So PV equals nRT. That's on the left-hand side. And on the right-hand side, we just have 1. So for any ideal gas, any gas that follows this equation, if you multiply the pressure of that gas times the volume, you divide by the number of moles of gas that you have, the universal gas constant, and the temperature in kelvins, you should always get 1. So for any gas, we could in principle go out and measure these 4 quantities: pressure, volume, number of moles, and temperature. And we can plot that on the y-axis. So that's what I've shown here. Now here's the special value 1 that I've drawn as this dashed line, and that would be the ideal gas case. Now here I have the experimental values that I've kind of sketched in for 3 different common gases. So hydrogen gas, carbon dioxide gas, and methane, CH4, which is the principal component of natural gas that we burn in our homes. So what you see is that at low pressure, all of these gases have a value of PV over nRT that's equal to 1. In other words, they follow the ideal gas equation as long as the pressure is pretty low. Now once we start ramping the pressure up, and these pressures are pretty high, right? So once we start ramping the pressure up, we see that they begin to deviate from the value of 1. So carbon dioxide really goes downhill quick. So it has a large negative deviation at high pressure from the ideal gas value. So this term right here is often called the compressibility factor. So compressibility factor. And you can think of it this way, that it's a rough measure of how compressible a gas is. And so comparing it to 1, we're comparing everything to an ideal gas. So this green curve, at least down here in this region of the graph, we would say it's more compressible than an ideal gas. So why might that be? Well, it could be that, so more compressible means it's easy to push this gas together. Well, maybe under really high pressures, we could imagine that these gas molecules are attracted to each other, and so they begin to pull towards each other, right? So if they're pulling towards each other at least a little bit, then they don't make it over here to bump into this wall as often, and so their pressure goes down a little bit. So they create a little bit less pressure, and so they're a little bit easier to compress, so they're more compressible than an ideal gas because they like to stick together. So they'd be more compressible in this region. Similarly for methane, methane is a little bit more, not quite as extreme, but a little bit more compressible than an ideal gas under these higher pressures. Now when the pressure gets really, really high, so past here we see that carbon dioxide, for example, has a higher compressibility than the ideal gas. So that means it's harder to compress than an ideal gas. Well, why might that be? So at really high pressure, we might imagine that you're trying to push these carbon dioxide molecules on top of each other. So they're pushing back, right? As you try to push on top of them, they can't occupy the same space at the same time. And so as you try to push down with this wall, well, these molecules are sort of pushing back on each other at really high pressure. And so in this region, we would say that the gas is less compressible than an ideal gas because of repulsions. So up here in this region, where you're above 1, we're going to say that the repulsions between the molecules dominate. So here the repulsions between the molecules are greater than their attractions. Similarly, down here in this region, we're going to say, if your value lies down here, that attractions dominate, that they are more important. So attractions become more important than repulsions in this region. Now, if they're exactly balanced out, like right here, then you would have exactly the same kind of behavior as an ideal gas. So when the attractions and repulsions are exactly balanced, then you kind of start to behave ideally again at this one kind of unique pressure value. So the other thing that you notice about this graph is that different gases behave differently. So the curve for methane is different than the curve for hydrogen, which is different than CO2. PV equals nRT, we said earlier, applies to all gases regardless of their identity. But we see under high pressures that identity matters. So it matters which gas you're talking about because we have different behavior, different properties. So in fact, the identity of the gas matters. And that probably makes sense because different kinds of molecules are likely to have different kinds of repulsions and different kinds of attractions between them. And this is our clue that that might be going on. So what do we do about this? If these real gases don't follow the ideal gas equation, then is there an equation that they follow? And the answer to that in general is no. But we can write down equations that work better under a wider range of conditions. So we can have equations that work pretty well for real gases over a much wider range of conditions than the ideal gas equation. So one of those equations is called the van der Waals equation, and it was developed by Johannes van der Waals, who was a Dutch physicist and chemist, and he proposed this in his doctoral dissertation. So it's very famous, and he went on to win a Nobel Prize for this work. So this is very important stuff. So he proposed this equation. We're going to talk a little bit about how it might come about. This isn't exactly van der Waals' derivation or proposal rationalization, but it's one that might make some sense. So let's start out with our old friend, the ideal gas equation. PV equals nRT, and I'm going to solve it for P, so P equals nRT over V. There we go. Now we know that this equation doesn't work very well under all conditions. So one of the reasons is that first assumption that molecules have negligible volume breaks down under certain conditions. So once we get the pressure really high, then the volume occupied by our molecules is actually a substantial fraction of the volume of the whole container. And what's true is I can't take this molecule right here and I can't put it right on top of this molecule over here on the right. In other words, this volume right here is excluded. It's like a no-fly zone. Don't go there, right? So you can't put this molecule, molecule A, you can't put it right here where molecule B is. They can't occupy the same space. So van der Waals might reason that, hey, we don't really have the whole volume of this container that's available for us to put gas particles, because there's some space where there are already gas particles and we can't put them there. That's our no-fly zone. So let's reduce the volume by the amount that is equal to the volume of all the molecules in our container. So this is what van der Waals proposed. He said we're going to take nRT and we're going to take the total volume of this whole space, V, and we're going to subtract from that the volume that's occupied by the molecules. So that's going to depend on how many molecules we have. So we're going to say minus, reduce this total volume by the space that's occupied by these molecules. So we need to know how many molecules we have. So that's N, the number of moles of molecules. And then we need to multiply it by some parameter that we're going to call B. So B is a parameter that's going to depend on the identity of the gas. So carbon dioxide, hydrogen, methane will all have different van der Waals B parameters. And B is kind of, I've heard it described as the bigness parameter. So what is the size of your molecule? So bigger molecules are going to occupy a bigger volume. Makes sense, right? So we need to account for the bigness of the molecules. Also, in some sense, this B term is related to these repulsions that I was talking about before. Right? So the reason that I can't put an A molecule on top of a B molecule is that the B molecule is going to repel the A molecule when I start getting them super close together. So that's why I can't put A on top of B, because they repel each other. All right, so this is taking care of repulsions. So this is the first correction that we can do to our van der Waals equation. So if this is due to repulsions, we must have some term that's due to attractions. So if we're thinking about attractions then, what's going on is we've got all these gas particles and they're buzzing around in our box according to the kinetic molecular theory. But if they're attracted to each other, we might imagine that a little bit they tend to stick together, right? So they're maybe like imploding or moving towards the center of the box a little bit, just like gravity would tend to attract clouds of dust in space together. These particles might be attracted together a little bit. Now, of course, they can break free and bump into the walls. But what this means is that our pressure that we would observe, POBS for observed, is going to be less than the ideal gas pressure, right? So in the ideal gas situation, we have no intermolecular interactions, so these molecules are free to come up and bounce against the walls as much as they want. But in a real gas situation, these molecules might be pulled towards each other, so they're not bumping against the walls as fast, as frequently, and that's going to reduce the pressure. So the observed pressure will be less than the ideal pressure. So if we go back over here to this equation, van der Waals realized that, hey, if I need to account for attractions then as well, what I need to do is reduce this pressure. So he subtracted another term. Then he has to figure out, well, what does this term depend on? Well, it's going to depend on two things. It's going to depend on all these attractions, and that depends on how many molecules you have. And really it depends on how close the molecules are together. So if the molecules are really close together, they have a better chance of attracting each other. Interactions between the molecules are going to depend on the density, N over V, right? How many molecules we have per unit volume. So the attractions are going to depend on that. And then we also have to think about how often do those molecules collide with the wall. Well, that also depends on the number of molecules we have and the volume. So these two factors are related to the attractions. And so van der Waals reasoned, and this wasn't exactly his reasoning, that this term has to go as N over V times N over V, or N squared over V squared. So he has a term that looks like minus A, so it's minus because we have to reduce the ideal gas pressure, which what we started with. We have to reduce that pressure due to the attractions. So A is the term for the attractions, and then it's A times N squared over V squared. So this equation then is the van der Waals equation. And just like before, this new A parameter is also going to depend on the identity of the gas. So different molecules will have different kinds of attractive forces, and so we need to account for those with the A term. So the bigger this A term, the stronger the attractive forces between the molecules. The bigger the B term, the larger the molecules are, the larger their excluded volume is. Sometimes you will see the van der Waals equation rewritten this way. So you'll see P plus A N squared over V squared, and that term will be in parentheses. And then there will be V minus NB, and that all equals nRT. And if we think about our ideal gas equation, PV equals nRT, then this new equation kind of has a similar form, right? So there's a term that involves pressure. There's a term right here that involves volume, just like over here we've got pressure times volume. And then there's an nRT term on the other side that involves temperature. So we've still got those three components. All we've done is correct the pressure and correct the volume due to attractions and due to repulsions. So let's do a quick problem. So in this problem we're going to imagine that we have half a mole of gas, and the gas in particular is going to be N2. And that gas is at a temperature of 300 degrees Kelvin, which is very near 25 degrees Celsius, so close to what we call room temperature. And we're going to imagine that this gas is contained in a volume, a 600 milliliter container, so that's 0.6 liters. And we want to know what is the pressure of this gas. So the other thing that we can do is we can look up the van der Waals A and B coefficients, and these are things that you can look up in tables. And remember, they're going to be different for every gas. And for nitrogen, the parameters are for A, that's our attractive term, our traction parameter, 1.35, and in these units, liters squared times atmospheres divided by moles squared. Now in different tables, you might see these values in different units. We also need to look up our B parameter. That's the excluded volume or bigness parameter, and it's 0.0387 liters per mole. And so this gives you sort of a rough idea of the volume that would be occupied by 1 mole of those molecules. So if you were to take out the space in between them and squeeze them together as close as they would like to be, they might occupy a volume of 0.0387 liters if you had a mole of them. So sometimes this is called molar volume, the volume occupied by 1 mole of stuff. B parameter is kind of close to a molar volume for a particular gas. All right, so we want to calculate this p-value. So one way that we could calculate the p-value is by using our ideal gas equation. So I'm going to write a little subscript IgE here for ideal gas equation, and that's just nRT over V. And we know how to do this. We would plug in all those numbers, and it turns out that that's 20.5 atmospheres. So under these conditions, we would have a pressure of that gas of 20.5 atmospheres, according to the ideal gas equation. Now what we want to do is also calculate this using the van der Waals equation. So I'm going to write VDW for van der Waals. So going back to our van der Waals equation, we're going to have to substitute in all these terms. So it's nRT over V minus NB, and then minus A N squared over V squared. So there's our van der Waals equation. Now we just have to carefully plug in all these terms into this equation. So we've got 0.5 moles times R, 0.08206 atmosphere liters per mole degree Kelvin, times a temperature of 300 Kelvin, and that's all over 0.6 liters minus 0.5 moles times our B parameter, which is 0.0387 liters per mole. And then we need to subtract from that A squared, 1.35 liters squared atmospheres per mole squared. And we're going to multiply that by the number of moles squared and divide that by the volume squared. So 0.6 liters squared. All right, so be careful with your squares here. Let's check out some of these units. So up in this first term, this mole unit will cancel out with this mole unit. The kelvins will cancel right here. Down here, this mole cancels that mole. Then we have liters minus liters. That's good. They have to be in the same units for us to add and subtract them. And then the liters here will cancel out the liters in this R term. And so the only unit that we have left is atmospheres. Well, that's good because we're trying to calculate pressure. The same thing is going to happen here. Our liters squared will cancel out. Our moles squared are going to cancel out. We'll be left with our unit of atmospheres. So when you're all done with this calculation, and you should plug this into your calculator and make sure that you get the same number that I did, we see that we've got 20.3 atmospheres. All right. So here we're pretty different from a normal atmospheric pressure of 1 atm, right? We're 20 times that. And you see that the van der Waals equation gives us a slightly lower pressure than the ideal gas equation. So why might it be that we have a slightly lower pressure? Well, if the P observed is less than P ideal, then that suggests that maybe attractions are kind of dominant in this case. So attractions are dominant, or dominate in this case, because that's causing the molecules to pull together a little bit, thereby reducing their pressure, because their pressure is less than what the ideal gas equation would predict. So if we saw the opposite case, where the observed pressure were greater than the ideal gas pressure that we would calculate, we might conclude that repulsions dominate. All right, so that's how we use the van der Waals equation, and you see that it gives us a very slight correction, but those corrections might be important if you're a chemical engineer designing a system that operates under high pressure. You don't want your system to explode, and so you need to know what actually are the pressures for those real gases that might be in your system. Van der Waals equation is one of many equations that we can use to account for the behavior of real gases, where we have to include things like the volume of the gas and the attractions and repulsions between the molecules.